Bismillahirrahmanirrahim. Assalamu alaikum. I am Fakhr Lodi and this is our 41st lecture of Formal Methods for Software Engineering. We have been discussing Z specifications. In the last lecture, we started to discuss the specification of an operating system scheduler. And what we are doing there is that, what we want to do is specify the OS scheduler in an abstract form at a high level using Z specifications, and then apply refinement to give it a concrete state. So the idea really is that we specify the system at a higher level and then apply the refinement steps. And each refinement step removes some of the uncertainty from the original specification. And it takes us closer to a concrete implementation of that specification. So Z specifications, they are not just helpful in specifying the system, but they are also helpful, and the techniques and the mechanics have been developed where you can apply these refinements, which are again part of Z, to give it a concrete shape. And remember that in Z specification, the most interesting feature of Z specification is that we can specify things in small chunks, then we can refine them, we can add new features, new things into those previously defined specifications. We can combine those specifications using schema calculus, and we can get through this process more robust and specifications for more complex systems. So we work in small chunks at a time, and that is where the real power of Z is. So in the last lecture, we started this specification for operating system scheduler, and we said that each process can be in 3 different states. It can be the current process, which occupies the CPU, or it could be in the ready set waiting for CPU, or it could be in the blocked set waiting for an IO or an event to occur. And we can have an up to n processes in our system, and each process will have a unique PID. So the PIDs are from 1 to n possible PIDs, and there is a partition that each PID can be accounted for. So either it is current, or in the ready set, or in the blocked set, or in the free set. So this is what we have, the set of PIDs, and it is a partition. That means the union of all these is the complete set, is the universal set, and the intersection of any 2 of these is going to be an empty set. So it is a partition there. And then we specified different operation on the scheduler, which included creating a new process, then dispatching it, then timing out, then putting it into the ready queue, putting it into the waiting queue or waiting set, and then waking up a process or deleting a process, all these different things that we specified. And we wrote small schemas for those specifications. In those small schemas, we mentioned that there was this uncertainty because we were not saying, for example, which process will be taken from the ready set and given the CPU when CPU is available. And Again, there was some degree of uncertainty that we did not specify which particular PID will be used when the next process comes or a new process is created. So all these different things. In order to give it a more concrete shape and form, we said that, the sets that we have, that is the ready set and the blocked set, they will be implemented using the concept of a chain. This chain is a linked list. We sort of given the specification of the linked list, and we started to talk about this chain and the different operations on that chain before we could apply that chain to implement the operating system scheduler processes, the functions there. So we were discussing the chain and its operations. So in the last lecture, we saw a few operations, especially pushing and popping from the chain. And we saw that there were several different cases. For example, when we pop, it could be the last element in the chain. So if there is only one element in the chain, what happens to the chain? If there are more than one elements to a chain, what happens to the chain? And then popping operation, we join these two schemas and we will get the schema. Similarly, we had the push. That is, when the chain is initially empty, then when we push, what happens? When chain has only one element, then what happens? And when chain has more than one element, then what happens? We needed these three cases because we said when the chain was empty, the chain, the links, the domains and the ranges, they were empty. So the relation links that we had, that relation was empty when there was nothing in the chain. When we had only one process in the chain, or when we had only one element in the chain, again, the start and end, they collapsed onto that single element, and once again there was nothing in the links. And when we have the third case, that is when we had more than one elements in the chain, at that point in time the relation links will have entries into that is that set will not be empty, and then we specified behavior in terms of those relations. Today we shall continue with that discussion, and we shall look at the rest of the operations for that chain. So let us go back onto the slide and look at the specification for the rest of the operations. So the next operation that we have is the operation for deleting an element from the chain. Delete, once again, has three cases. Remember, delete is different from pop, because pop means that we are removing this element from the front of the list, from the front of the chain. But when we delete, we will delete from anywhere in the chain. It could be from the start or from the end or somewhere in the middle. We needed this because we had the delete operation in our operating system scheduler, and that requires that we should be able to delete any element from the system. So here is the three possible scenarios. That is, we can delete from the start, we can delete from the end, or we can delete from the middle. The delete start updates chain. It takes a PID, and this PID is equal to start. And in this particular case, we say that the output of the pop operation, if we apply the pop operation, we get the same output that we get in the case of this delete. So this delete start is nothing but pop operation. In this particular case, what we have done here is that instead of rewriting the whole thing for our delete from the start, we have used an already written operation, already written schema, and that is pop. Since we had already taken care of a number of different scenarios in pop, and pop basically means deleting the first element from the queue or from this chain. Hence, delete start and pop, they are essentially the same operations. So instead of rewriting the whole thing again, rewriting the predicates again for delete start, we say use this pop. It will give us the output, and that output is the same as this is what the value that the PID that we have. So once again, see how did we use previously defined specifications. Instead of reinventing the wheel, we used the old ones. Now let us look at the second scenario, that is deleting from the end. Now this delete end updates chain. The input is a P, which is a PID. This is not equal to start, and this P, that is the ID for the process that we have given as input, is equal to end. So these are the preconditions. Now what we do is, when we delete from the end, we change this links by taking the element from the range of this links, the element that was present at the end. So we reduce, when we take that from the range, that means that is no longer available, and hence the set of links has one less entry. In this particular case, we are using a very similar technique that we used in the previous specifications. In the previous specification, we used the reduction of the domain. So when we reduce the domain or when we reduce the range, the effect of that is that we are effectively taking all those mappings that are defined on those elements. So if we take any element from the domain, for example, that means all the outgoing maps from that element to any of the elements in the range, those will be out because we don't have that element in our domain anymore. The same thing happens with the range. When we take something from the range, that means if there was an element that was mapped onto this element in the range, and there was a mapping that defined that relation, we will take that out because the other side is not available. So that means that entry will be deleted from that set of mappings or set of associations that define that particular relation. So this is exactly what we did, but in this particular case, we took this thing from the range. Why did we take this thing out from the range? The reason is very simple. The last element is not present in the domain of links because there is no next element going out or which is being mapped from this element into the system. So there is nothing after this one. So it is not present in the domain of links, it is present in the range of links. Now let us look at the third possible scenario, that is deleting an element from the middle of the chain. Once again, we have this specification which changes the schema chain, and it takes this P as the PID. It is not equal to start, it is not equal to end, and it is a member of the set. Now when we do that, when we want to delete this particular element, that means we need to delete it from the links. We need to delete it from the chain. So in order to do that, we need to make the previous one point to the next. The previous was pointing to this thing. So what we are saying is we reduce this links and we take this P out from the domain of links. That means it will no longer point to any element. There will be no mapping defined from here. And then we say that we define the previous of links, this links tilde P, that means this was the element in the domain which was pointing to P. Now that element points to links of P. Links of P is the element which was pointed to by P. So we took the element which was pointing to P and we make it point to the next element, and we added this to our set of associations in our relation links. Now once again, see, this is the straightforward simple operation that we usually perform on a linked list. The important thing to remember is that we are not traversing the list. We are not saying we are at P, go back to the previous element, because there is no way to go back to the previous element. We don't know how to go back to the previous element, but all we are saying is, in mathematical terms, take the element which was being pointed to by this, which was pointing to this element P. So we have this relation. We have, let's say, one element Q which is pointing to this P. Now we take this relation and we say, what is the source of this link? Go to the source of this link, which was Q, and what is the destination of P, link from P? We have this element R, let's assume. So we have this P, Q, and R. So we say, take the source and now take the destination of this links of P, make the source point to the next element. And this element P that we started with, that we gave as input, delete that element from our system. So by doing that, we have eventually deleted this element from the system, deleted this element from the chain. So there are three scenarios that we have looked at: deleting from the start, deleting from the end, and deleting from anywhere in the middle. So the delete, once again, operation, we can get that operation by combining all three of these. Since these are three possible scenarios, so we have the first scenario or the second scenario or the third scenario, and that is what we combine, that is what we do, and we get the specification or the schema for the delete operation using schema calculus. So here is the delete operation. Delete schema is equal to delete start or delete middle or delete end. Now when we have the definition or the specification for this chain available to us, we are not still talking about how to implement this chain, but we have given a concrete specification for the chain. We are going to use this chain in our operating system scheduler. We had 4 different places where a process could be found or a PID could be found. We had the current, there is only one process there, or at most one process, which currently holds the CPU. So it could be null also if no process is holding the CPU. Then we have three sets: ready processes waiting to get the CPU, blocked processes waiting for an event, and free. This is a set which has all the free IDs. Those could be assigned to new processes. So out of these four things, the current one is not a set. You can call it a set, but it does not have many elements. It has only 0 or 1 elements. So we don't need to have a chain there. The rest of the three, that is the ready, the blocked, and the free, these are sets, and we are going to implement or model these three sets using our chain. So what we will do is, we will take this chain, specification of chain, and we will create sort of instances of this chain for all three of these sets that we have, and then we will use these to build our operating system scheduler. So let me take you back to the slide and show you how to do that. So we have this ready chain. Ready chain is a chain with R start over start, R end for end, R links for links, and R set for set. Now this is another very interesting formulation and very useful one. Here what we are saying is that we are creating a schema for a new data type or whatever. So this is, let's say, ready chain. And in this particular case, what we are saying is, we are saying it is chains, but we are using the specification of the chain. We are using what was given in the chain, but we are giving different names to our different elements in that specification. Now the start becomes R start, end becomes R end, links becomes R links, and so on and so forth. Set becomes R set. So it is kind of parameterizing the old specification to get a new specification. It is a very similar concept that we have when we have the templates. In C++, for example, in generic programming, or when we have generic abstract data types, we have templates there. Those templates are parameterized, and then instances are created for that particular parameter that we have supplied with that template to create this new instance. Here we are doing exactly the same thing. So we will produce the other two in a similar manner. And as you can very easily see, all we have to do is we have to just give new names and replace the names of the elements that we are using in the original specification with our new names, and that gives us a new specification that we can use for our own purpose. So here are the other two, just to show you there is nothing very special about these specifications. So the blocked chain is we get by replacing start with start, end with B end, links with B links, and set with B set. So start with B start, end with B end, links with B links, and set with B set. So this is our blocked chain. And free chain, once again, we get by replacing start with F start, end with F end, links with F links, and set with F set. We have now instantiated these chains, but there are other operations that we need to specify. For example, we need to tell what is the initialization condition? What is the initialization condition for free? Very simple. In that particular case, we say that free will have the entire set. The set that we have has all the PIDs. What is the initial condition for the ready chain? In this particular case, it is a different initial condition. We have nothing in the chain. The same is true for the blocked chain. Initially, there is nothing in the chain. So for each one of these, although we have instantiated these schemas, we have created those schemas out of the previously defined schema by just replacing the state variables with new ones, but we also need to specify what happens when we initialize these things. So we need to write specifications for initialization, and we need to provide that information so that we have a proper initialized chain for ready, for blocked, and for free. So let us look at those specifications and see how we do it, although I have already mentioned what needs to be stated there, but let me show you on the slide what you will actually get. So this ready chain init is chain init where start dash is replaced by r start dash, end dash is replaced by r end dash, links dash is replaced by r links dash, and set dash is replaced by r set dash. Note one thing here, that we have done nothing really here. The initialization for the original chain that gave us the same kind of specification. That is, the set is initially empty, and all the other state variables that we have that define the state space of the system, they were given some initial values in our original specification, and we are saying in this particular case we will have very, very similar state there, nothing special. So same will happen with the case of blocked. So I will again create this thing, and we will get a blocked initialization for blocked chain, and it will have the same kind of mechanism. The only difference is that we have a different case when we have the free. In the case of free, it is not empty initially. If it is not empty initially, then we will have to write something there and give a new definition and new specification for that schema for initializing the free set. And what do we do? Let's look at it. So the free chain full has this free chain, and f set dash is equal to PID, which is the entire set which is initially full. We will now require push and pop operations on the ready and free chains and push and delete operations on the block chain. We define these by renaming the components of the corresponding operations on chain, just as we did a little earlier. So push ready chain, we get it by replacing start with r start, end with r end, links with r links, set with r set, and start dash with r start dash, end dash with r end dash, links dash with r links dash, and set dash with r set dash. Pop ready chain, exactly the same mechanism, the same formulation. And pop free chain, once again, exactly the same formulation. So what we need to do is, जिस तरीके से हमने initialization की थी, इसी तरीके से we need to specify or provide specifications for the other operations as well. So when we instantiate things are not automatically generated. We have to specify exactly what we need to do. So the other operations that were defined for this chain, those were push, pop, and delete. For our ready queue, we need to have the push, pop, and delete operations. And from our blocked queue, we need to have the push and the delete operations. These operations are defined for these queues, and what we do is, since we say the push, pop, and delete operations that we had defined on the original chain, they mapped exactly onto the requirements for these two chains. So we are not going to have anything different. The only thing is we are going to use different state variables, the state variables that we use in those specifications for the blocked chain and for the ready chain. So we will replace those and we will replace the original state variables by the state variables that we have used in these specifications, and we get what we wanted. So by just a process of replacement, we can achieve a lot in this case. And once again, its concept is very, very similar to the concept of templates that we have. We don't have to rewrite much of the specification. It would be probably much better if all these could be automatically generated, but that does not happen in this particular case. We have to specify which variable or which state variable is replaced by which particular state variable, and so on and so forth. But still, we don't have to rewrite the specifications. Another very interesting thing that you can think about is, especially when we wrote the specification of our free initialization. So if we do not take the original specification, we can give our own definition. That was the message there. So once again, it is a similar concept that we see in the case of inheritance. In inheritance, the base class is inherited by the subclass. So the properties, the variables, the attributes, and the operations, those are inherited by the derived classes. And if a derived class wants a different operation or different specification of the operation, it can rewrite its own function, and that will replace what has been written in the original base class. So this is a very, very similar concept here. Now let us go back onto the slide and look at the rest of the specifications. So we have the CS scheduler, which now has 3 state variables, and these are the 3 chains that we created. These are ready chain, blocked chain, and free chain. And current, once again, is the same as it is optional PID. It could be null or can have 1 PID. And chain store is a map from PID to optional PID. Once again, the current is, we have this current minus null PID, R set, B set, F set, and we define it as a partition PID. R links is equal to R set, chain store, R set. So we are defining the domain and range of chain store. B links, once again we have the B set as the domain and B set as the range of this chain store. F links, once again we have domain as fset and range as fset, and current is not equal to null PID implies chain store current is equal to null PID. So what we have done is that we have given the state of the concrete scheduler comprising the three chains together with an optional current process. It is also useful to identify the working space used. The component chain store is the union of the three chain functions plus an optional map to null PID. So you see how we now gave it a concrete shape. The original definition, specification of the scheduler did not have any concrete information about how to implement those sets or how these sets will be realized. Here, what we are doing is we created those chains, and now we say those chains are used in my scheduler. And I have given the entire scheduler. The entire scheduler has all these three chains, and the rest is very, very similar. So by just using what we have created, we have given it a concrete form, and it is a refinement step. Now let us go back and look at what else do we need to do on this particular scheduler. Initially, there is no current process and all chains are empty. So C scheduler init is we have ready chain init, we have blocked chain init, we have free chain full, and current is equal to null PID. Very simple and straightforward thing here. In order to initialize the scheduler, we need to initialize its data structures. So we have the two data structures which were ready and the blocked. They would be initialized to empty. The third one is the free, which will be initialized to all the PIDs, and that's what we have. And current is equal to null. So this is the partition. That was the schema predicate or invariant that we had. We cannot violate that, and in the case of initialization, that is what we get. Now we have C dispatch, which modifies the C scheduler. P PID, we have blocked chain and we have free chain. These are not modified when we have this dispatch. We have the same old requirement that current is equal to null PID. R set is not equal to empty. So we pop from ready chain and we say current is equal to P that has been popped there. So in the case of dispatch, once again we are giving it a concrete form, and we are saying that the ready and the free will not chain. They will not be modified. The only thing that is changing here is the current and our ready. So the blocked and the free, they are not changing. The rest is the same specification that we saw as the original specification in the scheduler. But here we have a concrete form. Let us look at the other schemas. Now we have this C create, which once again updates the scheduler. In this particular case, it does not change the blocked chain. The free set cannot be empty, only then can we allocate a PID. Current is equal to current, it does not change. Free, we pop from the free chain one element and it gives us the element at the top in the start, and we push that element, that PID, to be the ready, and that's what we have. Now in this particular case, see what we have done. Although the specification is very, very straightforward, but there is one specific point that I wanted to mention here. not only have we created a more concrete form of the original specification by giving it the notion of chains, that is, this is how we will implement this thing, but now we are also saying which particular PID will be assigned to this new process which is being created. The answer to that is very simple. Is it the smallest? Is it the largest? Is it which one? I don't know. I'm not saying the ID should be the smallest or ID should be the largest or ID should be in the middle. I'm saying the ID at the top, that is what I get and that is what will be assigned. So I have these IDs stored in my free chain, and these IDs, there is a linked list, there is a chain. The first one I take and I assign to the new process and add that process into my ready chain. And where do I add? I push it. So these are the things that now make it more concrete. So not just the data structure. The data structure, once again, at a high level, it is still abstract. We are not saying this chain, how will this chain be implemented? Will this be a linked list or will be implemented using dynamic structures or arrays or something else? I don't know. But I am giving it concrete shape, and I am giving it from a functional point of view concrete shape also. Now what we have to do is we will have to do this process and repeat this process for the rest of the schemas to complete my specification of the operating system scheduler. So what we do here is slowly take each schema and we see what kind of modification need to be incorporated in that schema. Sometimes we can simply create new schemas by replacing the state variables with new state variables, just the names. Sometimes we need to specify new predicates, give new predicates that give us the required functionality or required sort of behavior. So whatever we need to do, we do that. And by doing that, we come closer to the implementation. In this operating system scheduler, in this example, not only did we see a number of refinement steps. Actually, we refined the original specification by adding the concept of a data structure chain to implement different sets that we had. And then we also provided refinements for the operations. So it is not just the data structure, but also the operations that we applied, that we specified, and we gave slightly refined new meanings. And if we keep on doing that, we will ultimately reach a point where we can have an executable specification, a specification that can be compiled and code can be generated out of that. At this point, it is still vague because we did not talk about concrete specification, how to implement our chains. And there could be several different ways to do that. We did not talk about how to actually go from one element to the next in the chain, the iteration over the different elements in our linked list. We are not defining that. We have not done that. So we will be doing that. We need to do that in order to complete the specification. The discussion on Z is a lengthy discussion There are many different things that one could talk about, and this discussion could go on. In fact, there are at many places this Z has a one semester complete course on it, and people talk about different dimensions of these specifications and refinements and so on and so forth. But obviously we do not have that much time, so we have to conclude our discussion on Z now, and that is what we are doing. So before I wrap up, let me just briefly go over what we discussed. Z is a model-based specification technique. In this, what we do is we define the system behavior in terms of the state space. So we define the state space of the system, and the system behavior is defined using what is called schemas. So we have the state space, and then we have the predicates that define the restrictions or the invariant conditions on our state space. So that is what we initially do. Then for each operation, we specify how this operation changes the state of the system. So we specify whether this changes the state or it does not change the state. So we have some notation for that to represent that kind of behavior. And then for each operation, we define the predicates that tell us what exactly happens. The most powerful concept in Z is working with small specifications, working with small schemas, and then joining those schemas through schema calculus to give more complex specifications. Also, we can enrich previously defined schemas. So enrichment is there, joining is there, and from the previous schemas, we don't need to reinvent the wheel. We can join them together and we get specifications for more complex systems. Another very important, very useful concept in Z is the process of refinement. A refinement is a valid refinement if it is a consistent and correct refinement. What is meant by consistent? That is, if the original specification, this new refinement should not violate any of the invariants or any of the conditions in the original specification. It may take some of the ambiguity out, some of the options out, but it still remains within the universe that has been defined there. So degree of uncertainty is removed slowly by applying these refinements, and we can check whether these refinements are consistent by using things like backward or forward simulation. And then these refinements can be incorporated slowly. We have one step at a time. We use these refinements on small schemas, and we create small schemas, and once again, from those small schemas, we build larger schemas. And this process ultimately ends in a situation where we can have the specifications which can be executed and compiled. So that ends our discussion on Z. Inshallah, in the next lecture, we will start a new topic, and that is how to specify concurrent and real-time systems. Till that time, Khuda Hafiz or Assalamu Alaikum.